Nobody knows. Recording in progress.
Good morning. How are you this fine day? Although it is kind of dark and gloomy outside. Well, we're going to pick up where we left off last time and talk about finite state machines and regular expressions. I do have some warm-up problems for you to try. Might as well get right into it. If you remember from last time, introduced you to the idea of regular expressions, which is basically a way to symbolically represent a finite state machine. You've got three things that you can use to build your regular expressions in finite state machines. You've got sequencing, in which you just put some symbols right after each other, and then you represent that in your finite state machine as just a sequence of states. You've got alternation. You can either do branch A or branch B. Alternatively, you can write it as two branches going to the same state. And you've got this looping construct. So I've got two regular expressions here, and I want you to do two things. I want you to write out some examples of the strings that these regular expressions accept. And then also draw the finite state machine that corresponds to it. So why don't I give you a couple of minutes to try it out. And then those of you who are on Zoom, what you could do is after you draw your finite state machine, you could maybe take a picture of it and then post it in the chat. And then I can take a look at it. And maybe at the very least, if you want to get just started, maybe you don't know how to do the finite state machines just yet, then let's start by just writing out a few of the strings that these regular expressions would accept. You can post those as well. So if you're just tuning in, we've got some regular expressions here. We're writing out the strings that these regular expressions accept, and then also drawing the finite state machines for each one of these. You got anything yet? All right, we got some people posting answers to the first one, at least for the language. This one's pretty easy. There's only 3 possible strings it accepts: A, B, X, Y, and Y. I'll try the second one. Okay, the second one does accept AC and BA and BA, BA and BA, 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 and kind of an infinite number of those, but there's one more. There's one more that this one accepts.
Nothing.
Yep, very good. This one also accepts the empty string. How do you get that? You get that because the star here means I can do 0 or more of these things. And so if I do none of these BAs, then I just get the empty string. Good. So let's move on to drawing the finite state machines for each one of these. Still working on them?
I've got something, but I don't have a way to put a picture up. I guess I could turn my camera on and show you.
Yeah, just hold it up to the camera.
Let's see.
It's gonna be inverted. Oh, it's not.
Alright. Unfortunately for me, they're like little thumbnails, but I think I got the idea. Yeah. Oh, Sean, can I see that bottom one? Yeah. Yep. Okay, looks good. Okay, so looking at the few that got posted, there are a couple ways you could do number one. There's no right answer. I mean, there's wrong answers, but there's several ways to do the right answer. I'm gonna turn off this music for now. There we go. So one way you could do number one here is we could actually just do three separate branches. We could. I'm actually going to move this up here because we need some more space. So for number one, we could do it like this. We could have our starting state, and then we could do A over here, and then B, and then an accepting. And then here we've got an X, and then a Y, and then an accepting. And then finally we've got just the Y and an accepting. So that's one way you could do that. Another way could be to do an A and then a B and then the accepting, and then all the others just lead toward that accepting as well. You do like this. Or some combination of those. You might have one branch going off to an accepting and then two other branches going off to the same accepting. You know, as long as you end up on an accepting state, I think you're all right. And then for the bottom one, well, we've definitely got an A and a C that leads to an accepting. That handles this case here. And then we want to do this one here. We've got 0 or more BAs. So we can do it like this. We've got a B here. And then we could loop back and make an A like this, and then make this an accepting. But there's a problem with this one. There are actually some strings that this machine accepts that this finite state machine does not accept. You see the problem with it?
Yeah, we could do BAAC.
Yeah, this one will allow you to do like a BA, and then, you know, once you get back here, come over here and do this one. So that poses a little problem. So how do we address that?
You could take the BA branch at the bottom and not initially loop it. So it could go B to A, and then from that final A, you could have another BA loop that returns to it.
So we do the B here, and then we do a loop here.
And then loop from, yeah.
Like that. Right, and then where does the accepting go? Does it go...
The rightmost point?
Goes all the way in this one? The rightmost one?
Yeah.
Good. All right, so then we can do...
And then you need your
we need more accepting.
accepting on the initial starting point too.
Good. So we can either do AC, and then we just stop there, or we can do BA and stop there, or we could do as many pairs of BAs as you need, and we'd stop there, or we could do none, in which case our accepting would just be our final state as well. So that's good. Very good. So I got a couple more. Same idea. Come up with a few strings for the language. Sometimes that helps you find the patterns. And then draw the finite state machines. While you're working on those, I'll turn the music back on. I wonder if there's something else I could play. Oh, here we go. So for number 3, just to help you out here, so this or right here means that we're either going to do the left-hand side or we're going to do the right-hand side, but not both. So either the left-hand side or the right-hand side. So some strings that this accepts would be just A, which we'll get by doing the A here, and then no B's. And then we could do an A and a B, and an A and a B and a B and a B. And then that, keeps going on. Alternatively, we could do the right-hand side, in which case we got just a C, which we can do by getting the C here, and then no A's. We could also do CA and CAAAA. We can do CB by doing the C here and then the B. And then the or here inside the parentheses means we could actually switch back and forth between these two. So we could do CBA and CBBAB and CBAAAB, CABABA, right? So we can just basically switch back and forth between these. We can also do
Are we sure?
CBB. What's that?
I wouldn't C and then or B
Oh.
imply an end state.
I'm sorry, you are absolutely right, right? I was thinking the star was out here. It's not, it's inside. So let me back up. Let me back up here. So we got definitely, yeah. Thank you for correcting me. So we got just the C,
Yep.
we got CA and CAAAA, and then CB, and that's it. So you're right. So C and then just a B, or C and an unlimited number of A's, including none. And then for this number 4, we've got just 3 things that accepts. We've got x, y, z, y, x, and x, y, x. And we got some drawings yet? All these cameras suddenly turned on. Let's see what we got. Oh, Sean, that's an interesting one. Uh-huh. Okay, all right, all right. Sanjot, how does yours do this? Just the what is it? The YX.
I wrote it at XY. That's what happened.
Ah, okay. Okay. All right. So for the first one, we could do it like this. So it's basically going to be. Let's see. We could start here, and then we'll handle the A, and then an unknown number of B's, including none. Okay, so that's this one here. That part's easy. And then for the other side, we've got a C, and then here's our A star, and then here's our B, and we can make this an accepting and this an accepting. Okay, so we can do an A just by itself. We can do an A followed by an unknown number of B's. We can do just a C. We can do C followed by any number of A's. And then we can do a C followed by a B. But this one has a problem. I can see it's got a problem now. What does this one accept that is disallowed?
CAB.
Yeah, this one allows CAB. And we need to prevent that from happening.
Break that A loop.
How do we do that?
Give it one directed node to an A, and then an A loop off of that A. I think.
Well, if we do that, we can't have no A's.
Yeah, we can. We can just stop here.
Oh, okay.
Yeah, so we can do just a C and then stop. We can do CA and then stop, or we can do CA and then a bunch of A's and then stop there. Okay, good. And then for the bottom one, I saw a variety. There's many different ways to do this one. I saw one that looked like, here's an X, and then a Y, and then an X, or a Z. I think I saw that one. And then down here would be Y, and then X. Okay, that's one way to do it. I saw another one that was kind of a variation on this one in which these just went to the same accepting state. So that would also work. And then I think I saw one that looked like this. And the nice thing about this one here, even though it's got a few more states than the one above, is that it's pretty much just a direct translation of what you see in the regular expression. You see an XYZ, which is this top branch. You see a YX, which is this middle branch, and then an XYX, which is the bottom branch. But this one has a little problem as well. Imagine that these state machines are kind of like underground caves with tunnels between them. So you've got these rooms, and you've got these tunnels that are connecting the rooms. And so you're standing here, let's say you're, I don't know, you're Indiana Jones, right? So you're wearing your fedora hat, you know, and you've got, of course you need to have your whip right here. And so you're standing in this room, and you see before you these three doors. And one of them is labeled X. The other one is labeled Y, and then this one here is labeled X. And your goal is, of course, to walk through the correct door because you want to end up in these accepting states right over here. So what do? Which door do you go through? Well, you've got this ambiguous choice here. Should I walk through this door labeled X, or should I walk through this door labeled X? And the problem is that you don't know which one's the correct one. You won't know which one is the correct one until you get all the way down to basically this room right here. So if you could look ahead and see what symbols were coming up next, then you could make the right choice. But a finite state machine is basically a greedy algorithm, if you will. It makes a decision right now, and then it doesn't backtrack. Once you walk through this door, you can't turn around and go back through the other one if you discover you made the wrong choice. And sometimes you might think, well, maybe the symbol that will tell me which one is the correct door to walk through is the next one. But the problem with this regular expression is that it's not. The first two symbols are X, Y, so you're not going to be able to tell until you get to the Z or the X to find out which door was the correct one. So you have this conundrum here. How do I figure out which door to walk through if I don't know what symbol is coming up next? And there's actually a way to resolve that. So we'll get to that in a couple of minutes. Or actually, will it be in a couple of minutes? No, it's probably going to be like next time. So that's something to figure out. But basically, the way to resolve it for now is just do something like this. We've got only one branch with one unique label for every room. You don't have this situation where you've got two branches with the same label. If that happens, try to figure out if you can kind of like merge them together and make them one. Okay, so this time we're going to go the other direction. I've given you a finite state machine, and I want you to come up with a regular expression. So here's the first one. Come up with a few strings that this one accepts, and then try to write a regular expression for it. Same thing for this one, and then same thing for this one. Quick as you can, try to come up with some of the strings so that I've got something to talk about. Otherwise, it's just dead air. It's just me sitting here on camera watching you. Okay, so we got some people posting the first one. So some strings here would just be A, B, C, or A, D. Okay, and then a regular expression for that would be a couple ones you could do. You could do A, and then A, B, C, or A, D. And then someone else posted A or B, C, or D, but that's not quite right.
Yeah, you can't end on A.
Yeah, this one here doesn't allow just only an A, so we could fix it. This one can be fixed.
Could we throw an or bar right after the A before the parentheses?
Like right here.
Yeah.
So that would mean it would be an A or
Oh yeah,
a
that
B,
doesn't
C,
work.
or a D.
Could you do an or bar and then an A before the parentheses? So two A's.
Say that again?
So I guess just put an or bar before everything and then just put another A on the...
Oh, yeah. Yep, that's a good solution. How about this one?
Keep forgetting about the empty set.
A followed by a B, C, or a D, or nothing. Try the next one. Okay, so the next one could be just m. Could be like mn, and actually you can do as many n's as you want. Same thing with the p's. You could do mp once, you could do mp several times. And because you always return back to the state, you could just keep making a different choice every single time. So you can switch off between the m's, between the n's and the p's. So I've seen several regular expressions posted. And I'll put them up here and we'll take a look. So here's 3 of them that have been posted. Which one do you think is best?
Mine.
I was going to say that.
Oh, here's another one. So will the first one work?
I think so.
Yes, I think they'll all
so
work.
M followed by N or P or nothing, and then loop that as many times as you need.
If that works, though, I have a question.
Mm-hmm.
So, like, when you're going through all the steps, technically you can do M, and then you can choose to do the empty set, and then you can choose to do N, and then the empty set, you know, and then
Yeah.
there's these empty sets in there
Yeah.
that in the string don't really come out as anything.
Right? That's okay.
That's okay. Okay, cool.
I mean, imagine this was a Java string we were putting together. So it might look like something like M plus N plus nothing plus P plus N plus nothing plus P. And then when you end up sticking those all together, what happens to these empties?
They just doesn't matter.
They just go away.
Yeah.
Right? So this whole thing just becomes M, N, P, whoops, N, P, P. Yeah, so even if you have some epsilons in the string, ultimately they just end up falling out. So that's okay. So that's okay. Okay, so what about the second one here?
I think it works.
Yeah, it'll work. We got a single M, and then we got as many N's as we need, and then we got as many P's as we need, or nothing, and then we can continue to loop that. So that'll work. What about the third one?
That will not work.
That's the best one, and it will work.
We got some differing opinions.
Because it's mine.
Yeah, I feel like that.
Just M, though.
All right, so how does this one do just M?
You just don't choose a N or a P.
Yeah, the star here means just don't choose any of them.
Oh, I forgot you could do that with the star.
Yeah. Star doesn't mean 1 or more. Star means 0 or more. So you could do M followed by nothing. Okay, and then we have one more down here.
I guess that one works too.
It does.
But it's redundant in the same way that the second one is.
So you got an m followed by any number of n's followed by any number of p's. So they would have to go in this order, but the stars here mean I could do none of them. So I could basically do m and then a bunch of p's, or m and then a bunch of n's. Or I could do m and then, in order to do something like this last one here, I do an m followed by an n followed by a p, which handles this one here. Actually, this handles m, n, p, p, m, n, and then two p's right there. And then in order to come back and do these ones over here, I do the star. I take advantage of the fact that it comes back. And I can pick off two n's and then a p, and I can keep doing that. So this one works as well. Which one of these do you think is the most straightforward translation of the finite state machine?
Forests.
Which one is that? Number 3?
I think it's the third one, right?
This one here?
No, I was the second one.
Second
Well,
one.
the third one is definitely the best, though.
This one here?
Could we go back to the previous example that required the empty set, just so I can see why that one required it and this one didn't?
You talking about the previous slide?
I think it was the previous slide, yeah.
Now what were we looking for here?
I guess it wasn't the previous slide. I don't know. I feel like, wasn't there an example where we needed an empty set in order to make it work?
Here's the first
I think it was the one that we did just before this one, and I think the reason for that is that it had no loops in it.
Oh, okay.
So there was no opportunity to do the nothing.
So it's something on this slide that I've got?
I think it's the previous one.
Or this one?
Yeah, I think the second one. This one.
Oh, we're talking about down here?
Mm-hmm.
So there's a loop here, which gives us the opportunity to do just nothing. And we handled that by making the final state and the initial state be the same. Okay, let's do number 3. Strings it accepts are x, y, and just y, and there's one more.
Empty.
Empty, yep, empty string. So as far as a regular expression, we can do x, y, or y, or nothing. So I think next time, and by the way, so next week, at least here now for some of the people watching on YouTube who are not in the United States, next week is Thanksgiving week, and we have Thursday is the Thanksgiving holiday, but we also have Friday off. But some schools give the whole week off, and some schools give only the Thursday and Friday off. And so Sierra College is one of those schools that gives only the Thursday and Friday off. So we do have our regular sessions on Monday and Wednesday. So on those days is when we will talk about how do we resolve some of these ambiguous cases where there's 2 doors leading out of the room and you don't know which one to take. And also how do we handle these things like these epsilons. And these epsilons can also create a problem because sometimes those also create ambiguity. You have like a door labeled A and a door labeled epsilon, and you don't know which door to walk through because you could essentially walk through that epsilon door for free, right, and not consume any symbols out of the string you're trying to match. So that also creates a problem where you don't know which door to walk through. And we'll resolve all of that. We'll basically show you how you can take a finite state machine that has those ambiguities and convert them into a finite state machine that does not have those ambiguities. So what I want to do for now is talk to you a little bit about programmers' regular expressions. So what we've shown here are regular expressions kind of like from a mathematical point of view, looking at the finite state machines. But if you want to do regular expressions in a programming language, what do those look like? So regular expressions are sometimes built into a programming language. Like in Python and Perl and PHP, there's ways to type in regular expressions and have them do pattern matching on things like strings. Also, the Unix or Linux utilities sed, awk, and grep are really designed to work with regular expressions. So if you've taken the courses where you learn about those commands, you've already dealt with regular expressions a little bit. In Java, there are regular expressions, but they are not baked into the language itself in the way that they are in Python, Perl, and PHP. If regular expressions are actually part of the programming language, the nice thing about them is that when you run the program or compile the program, it will catch errors in your regular expressions. It'll say, no, that's not a valid regular expression. For example, if you want to put a star in a regular expression, it has to be preceded by something in order for that star operator to work. Well, if you don't put anything in front of the star, that's a syntax error for a regular expression. So the languages that have regular expressions built into them will catch those things, and the languages that don't, where the regular expressions are part of a library, will not catch those things until you actually try to run the program. And so Java, I think, falls into that category where it won't catch errors in regular expressions until you actually run the program. So in these regular expressions, a character by itself is taken literally. So if you have just like, A, that just means try to match the letter A. And if you have A, B, C, you're going to try to match the letter A, followed by the letter B, followed by the letter C. So you can concatenate by just simply writing characters in sequences. And then finally, there are a set of what are called meta characters. Meta characters are characters that have special meanings. We've already seen a few of them, like the star, which means match 0 or more of the thing right in front of it. We've seen the alternation with the vertical bar, and we've also seen the grouping with the parentheses. But basic regular expressions, or programmers' regular expressions, have a couple of additional meta characters. They've got the square brackets, which are used to match one character out of a set of characters. For example, if I put A, B, C inside of the square brackets, it means match either an A or a B or a C. In other words, this is equivalent to A or B or C with the vertical bars. So this is just a little bit less typing. You don't have to type all those bars, but they are actually just equivalent to each other. It's just kind of like a shortcut for doing all of those. And then finally, there's one more meta character, and that's a single dot, which is used to match any one character. Okay, so I'm going to go back and talk a little bit more about these square brackets because those are really where people kind of like them. Like if you want to do any one digit, any one digit number, you can just write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that would be equivalent to 0 or 1 or 2 or 3 or 9, right? Same thing. You could also just do a single letter inside of the square brackets, and then it just matches that one letter. But really, this is kind of redundant. You could just write this as, now in this case here, this is actually the letter E. That was probably a poor letter to pick. Maybe I'll use Y, right? So if you just want to put a single letter inside the square brackets, you might as well just put the single letter by itself. Then you're just making extra work for yourself. Scott, you're right. The nice thing about those square brackets is you can also do ranges of letters. So instead of doing this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can do 0-9, and it's the same thing. It will just automatically expand this out to be everything from 0 to 9. You can also do ranges of letters as well. Okay, so keep these in mind. We got the dot for any one character, the star for 0 or more of the thing in front of it, the square brackets for matching any one character out of a set, the vertical bar for alternation, which means or, and then the parentheses for grouping. And this makes up what are called basic regular expressions, or BRE. Okay, so let's look at some examples. I want to write a regular expression that matches whole numbers. Numbers like 2, and 1, 2, 3, and 68. 100,000, or just 0. So in order to be able to write patterns like this, you have to step away from thinking about these as numbers and instead thinking about them as sequences of characters. Regular expressions don't know anything about numbers. They can't count. They can't compare two numbers and tell you which one's greater than or less than. All it can do is do pattern matching on sequences of symbols. So you have to take a step back, like I said, and think about these as what kinds of sequences of digits am I looking at in order to be able to match what I consider to be a whole number. And someone's already posted a solution. We got 0-9 followed by 0-9 and then a star, and that's good. So we have one digit up front and then 0 or more additional digits.
Is there a reason why we can't just do 0-9 star?
Because then it would accept a string that contained no characters at all.
Okay.
And for us, a whole number would have to have at least one digit in it. Now,
What about the
go ahead.
the Z? Shouldn't we have an or
Oh,
statement?
no, sorry, this is a 2.
Oh, okay.
It's a poorly drawn 2. Okay, how about words? Now, again, regular expressions can't evaluate whether the word that it matches is actually a real word. All it can do is just match sequences of characters. So we'll consider for now words like and, yell, but also nonsensical words like blarg and maybe just G and X, L, R, R, P, Q, right? So this actually would end up looking pretty similar to the numbers, except that you're doing it with letters. So we've got A to Z, followed by A to Z star. So it's got to have at least one letter, but then it can have any number of letters following that one. But what if we also want to consider uppercase letters? What if we also want to do and then maybe all caps? Or even lowercase followed by capital letters. How do we work that in?
Is it set up so that the characters are like lowercase a all the way through uppercase Z, or are they two different sets that
There are
you have?
two different sets.
Okay.
And the reason for that is if you look at the ASCII character set, whenever you have that dash inside the square brackets, it's really just counting from the first letter up to the second letter. So if I had lowercase a dash lowercase z, it starts here at ASCII character number 97 and goes up to number 122. So it just runs this little loop from this to this. If I do something like lowercase a to capital Z, then it actually comes up with a set with nothing in it, because the lowercase a appears after the lowercase z, and it doesn't count backwards, so it doesn't go from 97 down to 90. So you actually end up with nothing in it, because there's no way to count forward from a and wind up at capital Z. Now, if you switched it around and did capital A first, followed by lowercase z, then certainly it'll count up from here. It'll go all the way through the alphabet, and then it'll also include some symbols that maybe you don't want. So there's no easy, direct way to do all the letters from A to Z, including uppercase and lowercase letters. You do have to consider them to be separate sets of characters, but there is one little shortcut you can do. But I'm just letting you know you can't just do like big A to little z and have it work correctly. Okay, so if we want to include uppercase letters, we can do something like this. A to Z, or big A to big Z, and that takes care of our first letter. And then do the same thing again. Oops. Or okay, yeah, Paul's got it. And then there is actually one little shortcut. You could do it like this.
That was my question. Because it's already a collection of ors.
Yeah. So you can do it like this. Okay. But this will not work.
How does that third one down work?
This one here? So
Yeah.
it's the set of letters from A to Z combined with the set of letters big A to big Z. So it counts from little a to little z, 97 to 122, and then it also counts from 65 to 90, and just combines them all together.
And it works because there's an implied OR bar between everything in the set.
Yeah.
Okay, that makes sense.
Yeah, so this is like basically A or B or C or D or E or E, all the way up to Z, or capital A, capital B, or capital C, capital D, capital E, up to Z. Okay, good with that? Oh yeah, Scott is posting there that this is basically the same as saying like A, B, C, D, E, Z, and then A, B, C, D, E.
So when we're actually programming, do we just do A dash Z, or do we have to like type in each symbol?
When you're actually programming,
Mm-hmm.
you can do this.
Okay.
Yeah, and I'm putting no here again because the loop that goes from big A to little z includes some symbols in there that you probably don't want. I mean, it'll work, right? It'll capture all the uppercase letters and all the lowercase letters, but it will also capture square brackets, slashes, carets, underscores, which you probably don't want to include in your set. Now, in the United States, we have postal codes that are called zip codes, and they come in two forms. They can come either as 5 digits, or they can come as 5 digits, a dash, and then 4 digits. So they might look like 90210, or they might look like 90210-1234. Scott's asking, can we use the ASCII number of the character? No. No, you got to use just the character itself. Okay, so how do we handle this? Well, it's 5 digits, so we got to put those in. 0 to 9, 0 to 9, 0 to 9, 0 to 9, and 0 to 9. And then the other one over here is 5 digits. Yes, I'm going to write them all out. So the first one is 5 digits, and the second one is 5 digits, followed by a dash. Now, when you've got a dash inside the square brackets, it means do a range, and when you've got a dash outside the square brackets, it just means a dash. So the only time the dash has a special meaning is when it's inside the square brackets. Okay, so we got 1, 2, 3, 4, 5 digits, a dash, and then 1, 2, 3, 4 digits. But we want to be able to match either kind of zip code, either the 5-digit or the 9-digit one.
So we just slap an or on there.
Yeah, so we basically do this thing. Whoops, I didn't mean to draw that as a green line. This thing or this thing. Or we could do this one or this one. Should I write it out? I guess so. Now here's where you actually got to pay a little attention to this. It does make a difference whether we do the long one first and then the short one, or the short one followed by the long one. In other words, do I write out this long one and then do an or and then do the short one? Or do I do the short one and then an or and then the long one? So when the computer is trying to match the patterns, it's going to start with the left-hand pattern first and then try to do a match. And then failing that, it'll try the next one down the line. And then failing that, it'll try the next one down the line. So it's going to try them from left to right. If we list out the short one first, well, the long ones do match that pattern. We've got 1, 2, 3, 4, 5 characters, which are matched by this one. And so it'll match this portion of the zip code and kind of ignore the rest. But if we wanted to match the long zip codes, we should list it out first, so it'll attempt to match the whole thing.
Well, then don't you only need the long one?
No, because if I don't put in the short one, then it won't be able to match this one at all. Because it'll do 90210, and then it will go, oh, there's more stuff to match, and I'm not at an accepting state, so it'll reject this one.
Gotcha.
So from this point, could you do the quantity, the long one's suffix or empty set?
Yeah, we could do it like this. Well, so there's two ways to do it. Let me do it the long way first. Or oh, I'm running out of space. There. Okay, and then the other suggestion was do it like this. I need the equivalent of a rubber stamp. And in programmers' regular expressions, there's no epsilon symbol. So we just do it like this. Okay, so we got 5-digit zip code, followed by a dash and 4 digits, or nothing.
So does that mean that the string that you're trying to match can be longer than the actual match statement? And like as long as, okay.
Yeah, and it'll just pull out the piece that matches. It depends upon the tool you're using. If you're using something like grep, then it will just match. If any piece of the whole line matches the pattern, then the whole line matches. If you're using something like awk or sed, then it'll only match just the piece that actually matched. Right? So it depends on the tool you're using. Okay, so that was a lot of typing or a lot of writing. That's basic regular expressions. You've got dot, star, grouping with parentheses, square brackets, and the alternation. There are also what are called extended regular expressions, which gives you some additional meta characters. I've listed 4 of them out here because these are the 4 you're going to need for the assignment, but there's more. There's a few more than this. But extended regular expressions, or ERE, accepts plus, which means 1 or more, question mark, which means 0 or 1, or otherwise known as optional, and then the curly braces, in which you can put a single number inside the curly braces, which means repeat the previous thing n times, or you can put 2 numbers separated by a comma, and it means repeat anywhere from n to m to n times. So as few as m times and as many as n times. And these are called extended regular expressions because these meta characters really don't give you anything extra. They just give you shortcuts for some of the basic regular expressions. For example, if I do something like a plus, well, that means 1 or more a's. And I can rewrite that as simply a star. So the plus is really the same as the symbol written twice with a star. So it's just a shortcut.
Does this mean that you can't use the plus or question mark in your strings that you're trying to match?
If you want to actually match a plus or a question mark, you just put a backslash in front of it, and it removes the special meaning of those characters.
Got it.
Right, so that's called escaping. So if you have a character that means something special, you can put a backslash in front of it, and it escapes or removes the special meaning.
So would that then work? 2 backslashes would give you the backslash?
Yep. So the backslash itself is a meta character. So in order to remove the meaning of this backslash, you got to put 2 backslashes. Backslashes. So the optional one here, if I do a question mark, that's the same as a or nothing. So it could be useful for things like A to Z and then ing question mark. So I've got a word followed optionally by ing. Okay, so what we did over here, we did whole numbers, we did words, we did zip codes, and how can they be made simpler using these extended regular expressions?
The zip code could use the question mark.
Yeah. So here's our numbers. So we had 0 to 9 and then 0 to 9 star. And this can be rewritten as 0 to 9 plus. Words, we had little a to little z, and then big A to big Z. Again, star, and that can be written as little a to little z, big A to big Z, plus. Zip codes. We could do that as 0 to 9 repeated 5 times. Or 0 to 9 repeated 5 times, followed by a dash, and then 0 to 9 repeated 4 times. And then to combine them together, we could do 0 to 9 repeated 5 times, and then a dash, 0 to 9 repeated 4 times, question mark. Okay, so we got 5 digits, followed optionally by a dash and 4 digits.
If I forgoed those parentheses, would it optionally do the repeat 4 times? So would it be like repeat it 4 times or don't repeat it 4 times?
No. I believe the question mark would still apply to this, but then it wouldn't treat the dash as being optional.
Okay.
Then your zip
Got
code would have to be like 90210 dash.
It's a bit awkward.
Right. Yeah, so I'm putting it inside the parentheses so that I group it along with that dash.
Are spaces treated as an empty character or as their own? Sorry, what was that?
Spaces, literally spaces.
Okay.
So it is tempting to put spaces into your regular expressions to make them like more readable, but then it actually wants to match actual spaces. So you should.
How would we have a string to match that has something empty inside of it?
Like space star.
I mean, so we have like the option for empty set for an empty character, right? But it doesn't seem like when we're matching something that what we are matching can have an empty character.
Oh, right. So we use that epsilon to just kind of as a placeholder. That means in our regular expression we are literally matching nothing, but the string itself won't have those epsilons in it.
Okay, that makes sense.
And for the repeat m to n times, how does it determine how many times it's gonna repeat?
For the repetition, basically, if I had something like a 2 comma 3, or let's do 2 comma 4, that's the same as a or a or a.
Okay.
So it just tries each one of these and tries to match the longest. Actually, it'll probably do it in the reverse order. It'll try to match the longest one first.
Mm-hmm.
So the extended regular expressions are great because they give you some little shortcuts, but do realize that all of those shortcuts are just ways to do basic regular expressions and save you a few keystrokes. There's nothing the extended regular expressions can do that the basic regular expressions can't do, just with more characters. Okay, so let's look at email addresses. Email addresses, they look like username at domain. For example, my email address is profbbrown@gmail.com. Don't you all start spamming me now. So this is the username portion, and this is the domain portion. But the domains don't have to be just like 2 words. You've probably seen some domains that are longer than that. We could have support@bbc.co.uk. In this case, the domain is longer. It has multiple dots in there. So email addresses can actually be fairly complicated, and there is a regular expression that will match email addresses. Okay, this is what it looks like.
Yeah, clearly.
And that's because email addresses, actually, because they are historical in nature, they've been around since the 1970s. There are actually some kinds of email addresses that we just don't use anymore, but they still have to be supported by mail systems. So email systems still have to support these old style email addresses. We just don't use them anymore. So those are encapsulated in that really complicated regular expression. I don't want you to use that one for our purposes. I want you to use a simpler one. So we know for sure that the email address is going to be something at something. What kinds of things can go in front of the at sign?
Letters.
Letters, good. Anything else?
Numbers.
Numbers, uh-huh. Anything else?
I think underscores. Periods.
Yep. Have you ever seen dots? Like, Barry dot Brown. Seen those?
Yeah, whatever special characters are valid, but what is that list?
Well, it's basically these right here. But we're not going to go that complicated. I'll also include dash. And I'll say that's good enough for us. And then back behind the at sign, over here, what do you see back there? Certainly we got letters. Anything else?
I think you can have the same set of characters. Is that true?
No, underscores are not allowed.
Oh, I didn't know that.
But otherwise, it is pretty much the same. You got letters, numbers, dot, dash, and that's pretty much it.
And then you're required to have another dot. And then some letters, and then you got to loop that.
Well, as far as email addresses go, you don't actually have to have a dot in there. You could conceivably have an email address like Barry@Gmail. And those are probably actually coming up. They're coming up with, so just a little digression here. So in your typical domain names here, usually you have 2 parts, at least 2 parts. You have this part here, which is sometimes a company name or organization name, and then a dot, and then what are called top-level domains. TLD, top-level domains. Those are ones like com, edu, uk, org, us. And traditionally, it has just been a fairly small set of 3-letter domains like com, edu, net, org, and then some 2-letter domains, which were usually just abbreviations for countries. US for United States, UK for United Kingdom, CX for Christmas Island, CC for some other little island in the ocean. But they've just recently started expanding that top-level domain list to include some other things. You've probably now seen some things like, I saw one that's like code.ninja, ninja being a new top-level domain they've allowed. And .dev for developers. There's like vscode.dev. And so they're opening up these new top-level domains for companies to come and buy, and they can either dole out subdomains under it, so they can create like ninja, or I'm sorry, like vscode.dev. So whoever owns .dev can now sell off subdomains under the dev top-level domain. But there's no requirement that they do so. A company could just buy a top-level domain and just keep it and just use it. So I think Wikipedia here has a list of top-level domains here, the old traditional ones, like com, org, net, int, edu, gov, mil. But now they've opened up all these new ones like academy, accountant, arrow, agency, Amazon. Look at that. Amazon bought the Amazon top-level domain. I don't think it'll be long now before you can just go to, just type in your search bar or your address bar, Amazon. You don't type Amazon.com, just Amazon. And it'll go to their website. Applebot.apple. So there's a whole bunch of new top-level domains, and there's no requirement that there be anything before it. This list just goes on and on and on and on.
What's that column with all the donuts?
Donuts? There was a
There's
dot.
the fourth column in this is it's just donuts, donuts, donuts. Operator, registry. Okay.
So this is the company that bought those domains. A company called Donuts. So some companies or some organizations will go through and buy these top-level domains in hopes of someday being able to resell it, flip it, if you will, to someone else who wants to buy it. So they might buy this top-level domain for, let's say, $1,000 or $10,000, and then maybe someone will come along in a few years and say, I would like to buy .digital. I'll buy it for $20,000. And so this company will then make a little bit of a profit on it. So that's where we are here. There's no requirement that there be a dot in there, but there can be dots in there. So we've got letters, numbers, dots, and dashes. So
if you own a top-level domain, does that mean that you can sell off the subdomains?
Mm-hmm. Yes.
It's $185,000 to register it, and that might not go through. If you wanted your own new one, I just looked it up.
$185,000. So
yeah, and then about $25,000 a year in upkeep.
I was underestimating a little bit for $5,000. So I don't think that's anywhere in my future.
Yeah, I was curious, but it's not going to happen for me either.
Did you hear? This is another little side thing here. Did you hear this headline came out where in the next month or two there's going to go on sale, on auction, one of the few original U.S. constitutions. There's only like 30 in the world. There's the original one, which is on display at the National Archives, and then there were some reproductions made at the time. So they are original reproductions of the original one. So there's only about 30 of them still in existence. And one of them is going up for sale in the next month or two. And they expect it to sell for between $15 and $20 million. And I heard that there's a whole bunch of people that own cryptocurrencies, Ethereum in particular, who want to try to get enough together to buy one.
It's awesome.
So some people that own Ethereum or got in early and now have made bank on it want to get together about $15 to $20 million to try to buy one of these original U.S. constitutions. And then related to that, the Staples Center in Los Angeles is going to get renamed as well. It's no longer going to be the Staples Center. It's now going to be the Crypto.com Center. A Singapore company spent, I think, like $200 million for the naming rights to that center. So no longer going to be the Staples Center. Okay, so we're back to this. So we want to incorporate letters, numbers, underscores, dots, and dashes. So it'll look like this. Here's our letters. We can include the numbers as well. Here's underscore. And then because dots and dashes have their own special meanings, we're going to need to put backslashes in front of them. And then a plus, because we want one or more of those things. And then on the back side, we've got our letters, our dots, and our dashes, and then one or more of those. And I would say for our purposes, this is good enough. This is not perfect by any means. For example, this will allow something like support at ... .com. All right, just because the dots are included here. So it's not really going to reject things that are clearly not valid email addresses, but it might be good enough. Scott was bringing up in the chat, regular expressions are really great if you want to pull certain small pieces of information from these large files. So sometimes you've got programs that generate large amounts of data. Maybe they're measuring things, maybe they're keeping track of what's happening on a computer, and you just want some small piece of it. So you can write regular expressions to churn through these large files and just pull out the pieces that you want. And also, regular expressions don't know anything about numbers. Numbers are treated as just sequences of characters. So it can't do anything like match all the numbers from 1 to 50. Right? There's no easy way to do that. If you can nail it down to being a specific pattern that you can write, then you could do it, but you can't just do like 1-50 and expect it to work correctly. Okay, I want to take a break at this point. We've been here for an hour and a half, and then when we come back from the break, we'll go over the assignment for this week. And this is, I think it's the last programming assignment of the semester. And there's not actually a whole lot of programming to do. It's just a bunch of regular expressions to write. So we'll take about a 10-minute break, and then we will come back and talk about that. Okay?
Recording stopped.
Now, for those of you who are watching on YouTube, I don't know whether this will be of a whole lot of interest to you because you won't have access to the files. But I guess you could watch, and then if it ends up not being that interesting, I'll end up trimming it off for the real video that I post on YouTube. Oh yeah, Sean, I've got kids coming out at noon also, so I need to show you how to do this assignment, and then I've got to go at 11:30. All right, see you later. Oh, someone asked, is this a math stream? Well, sort of. It's a computer science stream, but we're doing mathy stuff. This is called Discrete Structures, which is kind of like an intersection between programming and math. So you've got the computer programming stuff, and you've got the mathy stuff, and then you kind of like group them together, and the stuff that overlaps between those two things is what we're studying. So you saw here how we did regular expressions kind of from a math point of view, with the diagrams and the symbols that use math symbols, and then we branched off into the practical programmer's regular expressions and saw where those two things overlap. We'll be doing more math stuff over the next couple of weeks. I think we have 3 weeks left in the semester. So we'll spend at least another week and a half studying how to transform a regular expression into a finite state machine in a way that the computer can do it, right? The way we've been doing it, at least today, was we kind of sketched things out and then tested them to see if they would work. But that's not how a computer would do it. A computer would follow an algorithm, a step-by-step recipe for transforming a regular expression into a finite state machine. So that's what we're going to study over the next couple of weeks, is what's that recipe? How does it actually do the transformation into something that it can then execute inside of an engine, a regular expression engine, to evaluate whether a string matches a regular expression or not. So that'll be coming up over the next couple of weeks. We have class Monday and Wednesday. If you happen to be out of town because it's a holiday week, then just catch the stream later. It'll be recorded as usual. And then we will probably end up with a week or so of just extra time at the end of the semester, since we don't have a final exam, where we can just talk about some extra stuff. So I have some ideas for things we could talk about, but we could go like more in depth into some of the topics we talked about earlier in the semester, or we could do some new stuff. We'll figure it out. The question is, do different programming languages expect regular expressions to be written in a particular way, or is there a standard or universal notation? There's pretty much a standard. Most programming languages support extended regular expressions and also an extension to that called Perl extended regular expressions. Perl compatible regular expressions, PCREs. And those include not only the symbols we talked about, the star, the plus, the question mark, the curly braces, but also some additional meta characters that make things like more complex pattern matching possible. And that actually, Perl compatible regular expressions can match things that basic regular expressions cannot match, because Perl compatible regular expressions do in fact have a memory. So they can do things like match curly braces. So for every opening brace, make sure there's a closing brace that corresponds to it. Perl compatible regular expressions can do that. Basic regular expressions and extended regular expressions cannot do that. But that library is available for anyone to download and use, so a lot of programming languages simply include that library into their compiler, and then bingo, they support Perl compatible regular expressions. There will be some minor differences, particularly in the way that regular expressions are delimited or set off from the rest of the program. The rest of the program has things like variable assignments and loops and conditionals, but then in the middle of that you've got this thing that looks totally unlike any programming language. It's got dots and stars and curly braces that don't correspond to things like variables. And so most programming languages have a way of setting off the regular expressions from everything else. In Java, you just simply put them in quotes. They're just strings. In Perl and PHP, I want to say that they use backslashes or regular slashes to set off the regular expression from the rest of the program. I know certainly for Perl that's the case. I'm fuzzing out on whether Python and PHP also follow that same standard. Oh, awk also uses the slashes. Sed also uses the slashes. So there's a reason why Perl, awk, and sed all use the slashes, because they're all kind of like based on each other. So you might have some differences on that, about how to set apart the regular expressions from the rest of the language. All right, see you later, Scott. Catch the rest of the stream later. Okay, let's bring it back. We'll finish up talking about the assignment for this week. And like I said, I think this is the last assignment for the semester, at least the last one involving any kind of programming. So let's take a look at it. So this is on our course page. There's 5 files to download for this assignment. There's the actual assignment itself as a Python notebook, and then 4 data files that you need. You can either download all 5 files separately, or you can download a zip file and then unpack it and then upload those to your Jupyter environment. So I've already unpacked them. I've got, where is it? Lab 8, regular expressions right here. And I've got these 4 data files. Let's take a look at those 4 data files first. So this context file is just a list of names, addresses, phone numbers, email addresses. They're all made up. They're all fake. So don't try calling any of these numbers. I just randomly typed stuff in. I've got this one here called program. This is a fake programming language. Again, I just made it up. In this programming language, I've made some things easier for you. The keywords like class, var, function, return, if, else, those are all capitalized. And then variable names are all lowercase. Everything else is pretty much as you'd expect. The next one, called Perl.txt. Now this is an actual programming language called Perl. And this is what it looks like. Some of it looks a little unusual. You've got things like @ signs and dollar signs interspersed. And in the Perl programming language, this is how it not only tells you what are variables versus function names. Variables always have a dollar sign or an @ sign in front of them, and variable or function names do not. But also, the dollar sign and the @ signs tells you what type of variable it is. Dollar signs are used for what are called scalar variables. Scalars hold one single value, like a single string or a single number, and then the @ signs are used for arrays. So you get type information along with a little symbol that tells you whether or not it's a variable or a function name. You got comments in here. Comments start with the hash mark character and go all the way to the end of the line. So there's a comment here, here, and here are comments. And this first line here is also a comment. Here's a regular expression right here. Here's a regular expression that just has a single comma in it, and there's the slashes that are delimiting it. I actually based this program on something that I had to do for our server, which was to read in a list of first name, last names, and student ID numbers from a file, break them up into the individual pieces, and then put them together to make default passwords. So the passwords are first initial, last name, and then last 4 digits of your ID number, along with some modifications if you have first names or last names that are shorter than 4 characters. So that's what I had to do. So this is actually a snippet out of an actual program that I wrote. And then finally we got a file called weblog, and this is about 13 or so lines out of an actual file that a web server produces. Every time a web browser requests a page or an image or any piece of media from a web server, a line gets written in a file that has information about the IP address that the user came from, the date and time it happened, and then what actual document they requested. So here's requests for PHP documents. Right here is a JPEG. And then there's a status code here. 200 means everything went okay. 304 means there was something wrong. And then the last digit here is how long that file was. So this is a 219 byte file, 270 byte file, 11,213 byte file. So every single web server does something like this. And this file is useful for people who run servers because then you can do statistics on it. You can do things like, what's the busiest time of day for my website? And where are most people coming from? Are they coming from the United States? Are they coming from other countries? What kinds of documents are people requesting more often? Do they request certain images or certain pages more often than others? So you can get all sorts of interesting statistics out of a file like this. So here's the assignment. So there's a reminder here about the meta characters. You've got star, plus, question mark, square brackets, dot, vertical bar, parentheses, curly braces, dot. Dollar sign is also a meta character. So if you want to match an actual dollar sign, you got to put a backslash in front of it. And then you got to put two backslashes if you want to remove, or if you want to remove the special meaning with the backslash. And a backslash can be used to remove any other special meaning. Some common regular expression snippets are any one digit, one or more digits, any one letter, three or more letters, an optional dash followed by some digits, any number of characters. Dot star is any number of characters, including none. So the first thing to do is just execute this first cell. This first cell will import the regular expression library, and it will also build a function called extract. You don't have to worry about what that function does, but it basically makes it easy to execute regular expressions on strings or files and then just display the things that are being matched. So just go ahead and execute that. Okay, so problem number one is we want to find all of the numbers out of that contacts file. Let me go look at that file again. Contacts. So we want to pull out all the numbers. So here's a number, and here's a number, and here's a number, and this is three separate numbers. Here's a number. These are two numbers right here. Here's a number, number, number. All right, there's a number by itself. So you want to pull all of those out of the file. So what would I replace this to do with? Just replace those four letters to do with a regular expression that would match numbers. Now we already kind of did that. Remember that? What is this one here? Numbers. So you could either do this pattern or you could do this one. Both will work. Execute that cell, and then you'll get a list of numbers. Now, if you forget to put the plus on there, then you get this. You just get single digits, right? So that's not what we want. We want the entire number. So make sure you put the plus on there. Problem number two, extract all the words in the text. So here are the first few words from that file. We went over already what that regular expression would look like, so I'll leave that up to you to put in there. Extract all the 5 and 9-digit zip codes. Keep in mind that 9-digit zip codes might have a hyphen in them, so the first few zip codes look like this. So we went over the solution to that as well. So you'll type that in. Just replace the to do with the solutions we came up with. Don't erase this R in front. The R for Python, you might think of it as meaning that's a regular expression, but actually it means this is a raw string. Every character in that string, except for the quote character, should be taken literally and not replaced with something else in there. So don't erase that R that's sitting in the front. Problem number 4, email addresses. Again, we went over a regular expression that would match email addresses, at least good enough for our purposes. So you'll type that in here. Tokenizing. Remember, tokenizing is breaking up a program into its individual pieces. So we're going to take that program.txt file and we're going to extract all the numbers in there. Keep in mind here that the numbers can be like 1.832, negative 2.547, 720, and so forth. So it's not just whole numbers. Now it's going to be floating point numbers. So what does a floating point number look like? Well, it could look like 123, or 123.45, or negative 123, or negative 123.45. So you can have positive numbers and you can have negative numbers. So you might think of this dash in front here as being optional.
Would the previous extraction function To just take out numbers, would it take out the left side and the right side of the floating points as like two separate numbers?
Yeah, it would pull out the 1, 2, 3 separately from the 4, 5. So you're going to have to incorporate something that will allow it to optionally start with a dash and then have one or more digits, and then optionally end with a dot and more digits. So it might look something like what the zip code one looks like. Problem number 6, extract all the identifiers. Remember, identifiers are things like names of variables, names of functions. So in this fake programming language, they are all lowercase letters. Now, problem number 7 and problem number 8 is tokenizing a real language. In this case, it's that Perl file. So you want to extract all the variable names. In Perl, variables begin with a $sign or an @ sign. And then the next character can be a letter or an underscore. And finally, the rest of the variable name can be letters, digits, or underscores. And in Perl, @_ is a valid variable name. It starts with an @ and the next character is an underscore, and then nothing after that. So here are some of the variable names that you'll see if this is working correctly. So it can start with a $sign or an @ sign, and then the next character can be a letter or an underscore, and the subsequent letters can be letters, digits, or underscores. Problem number 8, extract the comments. Comments begin with a # symbol and continue to the end of the line. They can contain any number of characters, including none. So I'll give you a hint. This regular expression is really short. You want to have a regular expression that matches the # character and then any number of characters following it. It'll automatically go to the end of the line if you wrote that portion correctly. So it'll consider each comment to be a separate pattern or a separate line that it matches. Okay, so this regular expression ends up being really short if you find the correct way to do it. So here's what it should extract, these 8 lines, if you've done it correctly. And then finally, web server log files. There's 3 problems here. Extract the IP addresses. IP addresses are 4 numbers separated by dots. Remember that a dot is a special character, so you'll need to use a / in front of it. So you've got number, dot, number, dot, number, dot, number. If you want to, and you know something about the way IP addresses are constructed, then you could be more specific about what the numbers are, but it might be good enough to just say it's a number. Extract the dates and times. They look like this. Number / month / year, hour, minute, second. So you've got number / word / number, 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 number. And then finally, problem number 11, extract the image file names. They end in .jpeg or .png. File names can contain letters, numbers, and underscores. We want just the file name. Don't want all this stuff in front of it. Just the file name. So you should end up with 4 that you extract: header.jpg, greetingsart.jpg, background.jpg, and footer2.png. So those should be the 4 you end up extracting. Okay, so that is an overview of the assignment. So a lot of these regular expressions, we've already come up with solutions in the course of going through today. A few of them, you'll have to modify some of those to get them to work, but I think you should have a lot of fun with this. This is kind of like solving puzzles, right? You've got this whole collection of strings that you want to sift through. You need to find a regular expression that pulls out just the information that you want. Nothing more and nothing less. Are there any questions before we call it a day? I don't hear any, so I think we're good. Now I've got to go pick up my kids from school. All right. Well, again, if you have any questions on this assignment, you can post on our discussion boards. You can talk to some of our lab assistants or tutors, and they can help you out as well. Or you can send me a message. But
Professor, I have a quick question
Yeah.
about. So I'm working on number 8. And I think that's the one you said was going to be really short.
Mhm.
What would I use to show the whole set of ASCII characters? Is that what would make that? Because I'm just doing the hash, and then I tried just uppercase A to lowercase z to include all the commas and whatnot, but seems like I would want to include like all of the ASCII characters.
So there's like hints here.
Oh, it's up there at the top. Okay.
Someone asking, are the deep dive assignments extra credit? Well, they're not extra credit in the sense that they're worth extra credit, but they will factor into your collection of work that you do over the semester. They're sort of optional in that case. Like they're not ones that are part of the standard curriculum for the course, so you can do those as extra ones. But if you do those deep dives, then that will factor more into our decision about what grade you get in the class. So in a sense, they are extra credit, but they aren't like worth points because there are no points, right? All right, folks, that's it for today.
Have a nice day.
Yep, hope you all have a good weekend.
Thank you.
And
Have a good
yeah,
weekend.
I'll see you next week. All right, bye-bye. And YouTube folks, thank you for joining me as well. We'll be back next week on Monday, Tuesday, and Wednesday. And then Thursday and Friday we have a holiday, so we'll have that day off, those days off. And I'm kind of expecting Wednesday to be kind of a light day because a lot of people will be starting their holiday anyway. So we might just meet briefly or talk about something that's tangentially related to the things we're talking about right now. Okay, so again, I got to take off. I got some errands to run, and I hope you all have a good day, and thanks for joining me. These were great questions that you asked, and we'll get a chance some other day to be able to do more Q&A stuff. Just ask away questions about computer science or going to universities here in the United States or anything else, and then I'll try my best to answer them. So take care, all you, and I will see you later online. Bye-bye.